hydrogen is the most abundant element in the universe and has been used by humans for everything from fertilizers to rocket fuel. In recent decades, hydrogen has emerged as a promising clean energy source with great potential to overhaul transportation and industry.
My name's Shannon Boettcher. I'm a professor here in the University of Oregon in the Department of Chemistry, and I'm the founding director of the Oregon Center for Electrochemistry. These are some students in our Electrochemical Technology Master's program that's training students in the foundations and applications of electrochemistry for energy. Hydrogen, of course, is a very simple molecule. It's two protons bonded together, H2. So why is that energy? Okay, it's only energy because we can take hydrogen and react it with oxygen. We have abundant oxygen in our atmosphere to make water. Hydrogen's explosive, right? You light a match, hydrogen and oxygen explodes. It's making water. That's a downhill chemical reaction. So we harness that explosion much like you harness the explosion in an internal combustion engine, which is the explosion of gasoline, a hydrocarbon, reacting with oxygen via combustion to make water and carbon dioxide. The nice thing about hydrogen is when you react it with oxygen, there's no carbons, no carbon dioxide is emitted. There's two important technological concepts. So first is making hydrogen in the first place. Where do you get the hydrogen from? And then how do you use it? How do you get energy, useful energy to run our civilization from it in principle? So making it historically, most hydrogen we use quite a bit of it in our economy today, but it's made from what's called reforming of fossil fuels. So you can get hydrogen out of a carbon and hydrogen molecule by releasing the carbon as CO2, and that leaves you with hydrogen. That's how most of our hydrogen is made today. There's, of course, now new processes that are efficient and can be run with electrical energy, electrolysis, to get the hydrogen from water, pulling the oxygen out, and just releasing O2 in our atmosphere. So then we have the hydrogen. Then what do we do with it? That's your question. How do we get energy back out from hydrogen? The simplest way is you burn it. It has a different combustion temperature. It carries different amounts of energy per cubic foot. There's some engineering differences. But from a chemical principle basis, it's very similar to any gas-based fuel source like you have in your barbecue, for example. Another way that's more efficient and would be used for situations such as running a heavy-duty truck, for example, is something called a fuel cell.
So hydrogen fuel cells are electricity generating devices that consume hydrogen, consume oxygen out of the air, make electricity for a number of applications. So Ballard is a 40-plus-year-old company. We've almost always been into fuel cell technology. Ballard has developed stationary fuel cell systems powering hospitals, data centers, telecom cell tower sites. More recently, we're into the heavy-duty motive application space. In fact, that's what we're building behind us, is a fuel cell module for heavy-duty buses and trucks.
Hydrogen doesn't make a lot of sense for light transportation, where you can use a battery. The batteries are good enough to run a small car or a pickup around a city or even rural areas these days. And they're just getting better. So probably hydrogen will have very little role in those applications. But applications where the amount of energy storage you need is so large, you couldn't possibly build a battery that big because it weighs too much. Then you have a huge need for synthetic fuels. And hydrogen is by far the simplest synthetic fuels. There are alternatives, but hydrogen is the simplest and probably most cost-effective, and what I think we'll probably see to the largest extent.
What is the FC Move HD Plus fuel cell?
We refer to it as a module because it's not just a fuel cell, it's a fuel cell plus things like coolant pumps, air compressors, valves, controllers, safety systems. It's ready to be integrated into a vehicle. It supplies the electricity to the electric drivetrain of a zero-emission vehicle. The fuel cell is actually a stack of a bunch of cells. We introduce hydrogen to one side of a cell and oxygen from air on the other. And there's a chemical reaction that goes on, and the hydrogen actually permeates through a membrane, combines with the oxygen on the other side to create water. And in doing so, there's an electron and an electrical current that's generated. And if you stack a bunch of those cells together, you end up with a substantial source of power. The fuel cells used in the product behind me have 220 cells per stack. So this is a 220 cell fuel cell stack, and you can kind of see from that angle how thin these plates are.
On this side of the module over here, we have these two compression fittings. So that's going to be our fuel in and then pressure relief. Air going into these butterfly valves and then coolant as well. And then at the very end of the side over there, there's a couple high voltage connections, and that's where the voltage output is going to be.
If you start with the idea that you have an electric vehicle with batteries, and you go to an application where you have to drive for an extended period of time, or you're carrying a heavy payload, you end up needing a lot of batteries, more than you'd like, right? And you're displacing your ability to carry a payload. So that's where fuel cells come in. You reduce the size of your battery bank. You're supplementing the power to the drivetrain with hydrogen sourced power. The batteries are simply there for peak power demand, like you're going up a hill or you're accelerating. And the fuel cells giving you that long-term steady power to make that long haul or carry that heavy payload. Primary customer here for our product is New Flyer. They're the largest transit bus manufacturer in North America. That's our customer base, is the heavy duty, long duration, or a customer who can't really tolerate recharging times for batteries.
Before we actually introduce hydrogen, we want to make sure that everything is operating as it should. So yeah, kick it on.
Yeah, fire it up.
Going on here is an end-aligned factory test. So every fuel cell module is actually operated through its full operating range. It has to achieve full power. The performance has to be, above a prescribed level.
So this basically simulates like the kind of power load that the fuel cell will have to deal with while it's driving a truck or something like that.
That's right. Instead of just burning the power and, running a heater outside, we actually are pumping that power back out onto the grid. So we're actually running our meter in reverse when we're running our tests. So,
nice.
Yeah.
So it reduces your power bill a little bit.
That's right. That's right.
This one right here is a fully complete module.
It's fully tested. So it's gone through our factory acceptance test and yielded the high performance that we're expecting out of it. So right now it's complete and it's basically being ready to put in a crate and ship to the customer.
And what does that name mean? FC Move HD Plus. I'm guessing FC is fuel cell. Move is a brand, but what's the HD Plus?
So HD just means heavy duty. The original heavy duty module was a 70 kilowatt module. And then we said, okay, we need 100 kilowatts. So we just added the plus. nothing too secret going on there. Each time we have a generational improvement, we're working on performance, durability, and cost reduction. Cost being key to having that kind of scale up of volume. If we go back a decade or so, we were using industrial components that maybe weren't tailored very well to our application. Today, with the interest in hydrogen technology and fuel cells kind of taking off, we have those tools and those components that we need that are very tailored to our application and more cost effective. We really appreciate the early adopters, the customers we have now that are buying these in low but increasing volumes each year. They're helping us achieve that scale each year, as we go from 100 to 1,000 to 10,000, get the economies of scale. At a certain point, we're on that curve, and it's just a matter of volume to get to the target price. Over time, as that infrastructure comes together, it enables the technology to be deployed. Right now, hydrogen mostly comes from natural gas. It's not super green yet.
So our team broadly is working in the area of electrochemistry. And, electrochemistry is anything where you have electrical current, electrons in a wire, interface to a chemical reaction. Many electrochemical phenomena, batteries in your laptop, that's electrochemistry. We're converting between electrical energy and chemical energy in the form of a battery reaction. But there's other forms of electrochemistry. One of the most important ones that we're working on is electrolysis reactions. This is where you drive uphill chemical reactions by inputting electrical energy, and it's a way to store energy for a long duration. It's a way to make chemicals that are useful. It's a way to make hydrogen fuels, for example. Okay, so these devices are very small scale versions of what industry is building enormous, we call them stacks, electrolyzer stacks. And they have, again, two electrodes, one making oxygen, one making hydrogen, and a membrane for the ions to pass through, much like we talked about. So we're testing really some new materials that are, in principle, much more efficient and much cheaper to manufacture in these devices here. You want to be able to build these devices, these electrolyzers, at a very large scale with minimal baseline costs of ingredients, right?
Hydrogen can be produced and used with carbon-free methods. But in practice, it can be a tricky resource to work with, legendary for its explosive flammability.
It's bursting the flame. Get it started. It's fighting, and it's crashing. It's crashing terrible. Oh my, get out of the way, please. All the humanity and all the predators speeding around it.
Hydrogen's tendency to ignite is well understood, and consequently, strong safety measures are employed when working with it. But for wider world applications, such as renewable energy, there are other risks and challenges to consider.
So here's a couple problems, right? So one of them is hydrogen leaks. There is some worry that if there's too much hydrogen leaks, it could cause some reactivity in the atmosphere that has some deleterious effects. I think this is something that needs to be studied more. And we need to improve our materials and monitoring systems. You may have heard a lot in the news about perfluorinated polymers. So perfluorinated polymers are plastics that have a lot of fluorine atoms in them. And these have great properties for the devices that make and use hydrogen. But they can contaminate groundwater. They're not easily decomposed. So they can accumulate. They can cause cancer and other things in humans. So we need to manage that. I believe that with sufficient oversight, just like any of our energy technologies, any of our human technologies, many of them have substantial downsides. This all has to be managed, right? But when you compare it to something where we are essentially digging out a complex mixture of a lot of different elements in hydrocarbons and burning them and releasing all that into the atmosphere, not just the CO2, all the stuff there, lead, other things, it's, in my view, far superior. Anything we do as a human civilization that's not a closed loop is eventually going to become saturated. Supply cannot meet the demand, we're going to run out, or we're going to put huge stress on our natural system. So what I mean by a closed loop is the inputs equal the outputs. So if we have water, we have a lot of water on the planet. We use the water, we electrolyze it to make hydrogen and oxygen. All we're putting in is energy. We're rearranging the atoms. Oxygen will actually be vented to the atmosphere, increasing the oxygen in the atmosphere. Somewhere else, different oxygen can be taken in from the atmosphere, can be combined with hydrogen to remake water. That water goes back in the atmosphere. Both water, oxygen, those are very natural substances. Those are the only things that, in principle, a properly operating system emits. So it's a closed loop. We're not burying anything. We're not depleting anything. We're just taking renewable energy. There's plenty of sun. There's plenty of wind to do all of this.
So these are the tanks where you actually store the hydrogen you use here in this facility?
That's right. So we're really fortunate. We were able to line up a supplier here in the Northwest, Airgas. This hydrogen's coming to us from Kalama, Washington. And actually, it's pretty green. They're generating this hydrogen from an electrolyzer.
There's lots of different ways to use and store hydrogen, and they're going to vary substantially based on the application. So hydrogen can be actually piped around at very low cost, much like natural gas. The challenge is you need different types of pipes because it's a very small molecule, and it can damage steels and things like that that are not meant to carry hydrogen. So it needs some infrastructure to pipe it around. That would be using it as low pressure. And that's what you do if you just wanted to use it for an on-site application, for example, in a steel mill or to any sort of high temperature process you wanted to run with hydrogen instead of with a fossil fuel. However, if you want transportation, you can't store enough energy in low pressure hydrogen. So what you would do is you compress it. So that requires a reinforced tank. There's high pressure tanks up to 700 bar. It's not too much energy to compress hydrogen. The final solution, which is in principle ideal, but it's very expensive right now, is to liquefy the hydrogen. It carries the most possible energy per unit volume. And that's very important in an application for like an airplane. So if we're going to have jets, which we probably will, jumbo jets flying off hydrogen, they're going to need liquefied hydrogen.
You can get like 4 times as much hydrogen in liquid form than you could in gas, even at, 7,000 psi. We'd love to have liquid hydrogen here, but there's certain setbacks related to a liquid hydrogen storage facility. And there's just not enough space between these buildings. Otherwise, yeah, liquid would have been the way to go.
We will need huge amounts of infrastructure. This is probably trillions of dollars, many trillions of dollars for world infrastructure. It's going to be probably 20 or 30% of our global energy market. That's a big job. It's not going to happen fast. It's going to happen slow. And it's going to happen over the next few decades. And we're going to start with the things where it makes financial sense. Investors can put money in and get a return on their investment. And that's where hydrogen is going to be seen to have a big impact in the next decade. Ultimately, the use of hydrogen depends on the economics, the cost of making the hydrogen, the cost of storing it. A lot of that depends on the scale. Almost all technologies, as you scale them, they become dramatically cheaper. Batteries, solar cells, cell phones, everything scales like this. So where are the immediate places hydrogen is going to have an impact? I'll tell you a couple really big ones. So one of them is fertilizer. We make fertilizer by taking N2, nitrogen from the air, and we react it with hydrogen. This is a chemistry that won several Nobel Prizes. This is how a huge fraction of the world is fed for synthetic fertilizer. Right now, that hydrogen comes from fossil fuels. It emits a lot of CO2. It's a plug-and-play replacement into that process to use green electrolysis-based hydrogen from water and renewable electricity. That's an obvious place to do, and that's a good 1.5% of the world's energy use right there. Other places where it makes a lot of sense is any very high temperature process. So a good example is steel. To heat up the iron and to mix it with carbon to make the products we need, right? So right now that emits a lot of carbon dioxide. Other areas that are very hard to get the carbon dioxide emissions out of with things like batteries is aviation. The physics don't really work for a battery-powered airplane. We'll see small local transport, small commuter planes, certainly, but it's going to be very difficult. It's going to be impossible to fly a jet from Los Angeles to New York on batteries. It's not possible. So that's going to probably be liquid hydrogen. Freighters is another good example. If you have a freight ship, probably liquid hydrogen makes the most sense ultimately. The companies that make the devices that produce hydrogen from electricity and water, they're growing very rapidly. Every year the costs are getting lower and their orders are getting larger. Innovation in manufacturing is coming big time in this area, and that's going to lower the costs a lot. Renewable electricity is getting cheaper, and electrolysis hardware is getting cheaper. Fuel cell hardware is getting cheaper. Hydrogen management structures are getting cheaper, but we have a long ways to go. A gallon of gasoline has about the same energy density as a kilogram of hydrogen. Kilograms, 2.2 pounds of hydrogen. Right now, it might cost you $10 for a kilogram of hydrogen. But it's a pretty clear strategy to get to $1 to $2 per kilogram. And there you're outcompeting gasoline costs, right? So that would be great. And I think we'll see that in the next 10 years or so. Part of this is driven by policy and by government programs, like the Hydrogen Hubs program from the Biden administration, which is sort of accelerating the deployment and de-risking technologies and local ecosystems that drive the deployment of production and use of hydrogen for the initial smart applications. They put aside $8 billion for hydrogen hubs. There's one here in the Pacific Northwest. There's one in California. They're putting money on the table to help industry get started, saying, look, if you put in 50 million, we'll put in 50 million, and we're going to build a plant that takes hydrogen made from electrolysis, and we're going to use that to make fertilizer, and the farmers in that region are going to use that fertilizer. That makes a ton of sense. You have a lot of wind, you have a lot of hydropower is another source of green electricity. We have a lot of hydropower in the Pacific Northwest right now. We have solar, we have all the things we need. If you're in the port of Seattle, and you want to de-risk hydrogen as a maritime fuel, it will be a great fuel, but we need the hydrogen, we need the ships. And it's going to be subsidized at the beginning, but most of the costs are actually still being borne by industry because they know ultimately there's a lot of money to be made in the new energy economy. It's just getting over that barrier. How do you displace bunker fuel, right? With the cost structure that it has. You need some help getting started. So it's subsidizing the cost, just like we actually subsidize gasoline costs. It's all subsidized by the federal government. So it's no different. It's just a different way of subsidizing things. It's very much how we built the interstates, right? The government comes in, builds the interstate system, it accelerates the economy. The foresight there, I think, is really good.
I think as those pieces come together, that's the secret to deploying fuel cells in large scale. Probably 5 to 10 year timelines, but it's not really a problem. That's kind of our timeline too for major fuel cell adoption.
One of the great things about the, American capitalist model is if there's money to be made, there'll be a lot of capital coming in to make that new economy happen. But you have to demonstrate that money can be made. And we'll see. It's still a tenuous case. The economies of scale aren't yet there. We're building towards that. It's going to take actually really international cooperation and competition to drive the prices down. We're not going to run the world on hydrogen, right? But we're going to run a piece of it on hydrogen.
If you go out and you look at a New Flyer bus, you might see, Ballard technology inside, something like that. And, there was a time when I maybe was not convinced that we could ever make fuel cells an economically viable product, but I'm more convinced now than ever. I mean, we are doing it. It's not a question anymore.